Hey Algebra 1, wanted to film the last video here in the series for the at home Algebra 1. So let's talk about when you were talking savings account, compounded interest, all that stuff has to do with exponential functions. And so when we're talking about the compounded annually formula, we could keep it real simple and just say, you have your principal, your starting amount. You have your ratio, how much you're multiplying by, and then you have an exponent that represents the time. And if you watch the other videos, you may notice that we had like a sub 1 times r to the n minus 1. That was one of our formulas for doing an exponential sequence. Well, that's really the same thing as what we got here. We have our principal, which is your initial amount, how much you're starting with. You have your ratio, which is calculated using the percentage rate in the problem. We do have to divide this number by 100 in order to get that decimal form out of the percent form. And then that n minus 1, I know I don't have the minus 1 there. That really is still representing putting a variable in the power in some form or fashion. And so that's why it's going to really follow this exponential curve. Or if it was losing money, which this one's actually saving, so we kind of know it to be more, increasing. If we were losing money, we would see it go down exponentially, basically the reflection of that graph. So this formula could be, compounded more than once a year. It could be compounded semi-annually, twice a year. Could be monthly, 12 times a year. Could even be weekly, 52 times a year. It's good to know all of those. 365 if it was daily. But basically that would mean that it's going to calculate how much interest you have more often and add that on more often. And so when you continue to do that, basically it helps the money increase faster, and that's why banks don't really do it. Compounded is a lot of times used in science because when we're talking about how fast a plant grows or how cells are decaying or growing, a lot of nature, it's more of an exponential concept that we really want to study. And so that's where the compounded eventually constantly or continuously in Algebra 2 becomes way more interesting. And so right now we're basically saying it's annually, once a year. And so I could say, well, n is 1. I'm doing it once a year. But dividing by 1, multiplying by 1 doesn't impact the formula. So if you were to look up what is the compounded annually formula, you may see it as simple as this. So it basically says we have $1,500, and that's kind of like our a sub 1, if you will. That's like our starting amount. And we want to look at that and say, well, let's plug in 1,500, and then the R value, I want to add 1 to this. Making it grow, it has to be a value greater than 1. If you multiply by 1, it doesn't change, so multiplying by less than 1 will make it decay, and so 1 is that barrier. That's why it's kind of in the formula as adding or potentially subtracting if you were losing money. But basically that gets kind of shoved into your formula. T represents how much time goes by, and if you read in the problem, basically it just says a function of time in years t. It doesn't tell us a specific amount to plug in. Again, we're trying to write a function here. Savings S, so this basically is like savings based on time. That's how you kind of think of this. The way you say it is S of t. Now there's one other part that I want to mention. It says that he also has $200 in a safe at home that he doesn't touch or add to. And so basically that money is not changing, but if you're calculating his overall savings, you want to maybe take that into account. So he's got this $1,500 situation where he's getting 2.8% annually, and then he's got this other 200 he wants to add to his money, and this is how his formula is derived. Let's look at another one, and this will be the last one for today. I will talk a little bit more about domain and range using the calculator here in a moment, but hopefully if you think those ideas are tough, hang in for the very end of the video and maybe you can kind of learn something about domain and range you didn't know. So it says complete the table to determine the corresponding points on C of x. And so if you really look at this, they start by giving you a function 4 to the x power. And so we've got that graphed right here on our axis in black. And then it says, well, c of x, that would be the same function. So imagine, 4 to the x, but I want you to subtract 1 from it. It's the same function, but like 1 less. And so you can kind of imagine when I'm trying to figure out new points, I'm going to start plugging in 0 and 1, just like I did to get the other function. But now I want to know, like, well, how does that change the graph? So when you plug in 4 to the 0, you get 1, and 1 minus 1 is 0. So that means you're getting 0, 0. And that's a point on your graph. Well, then I want to plug in the value of 1 here. And so when I plug in 1 there, you see 4 to the 1 is 4. 4 minus 1 is 3, meaning you now have, when I plug in 1, I get 3. So 1, 3-ish is a point. So I know the axes are here are a little weird because they're going by 2s and I'm trying to do 3s, so it's kind of estimation. You can use a graphing calculator or even a website like desmos.com to really explore that a little bit. And so really, if you think about where those points were, basically the graph is just shifting down 1 unit. And that kind of follows in the other videos. We were kind of talking about how if you have a number out front, that's called dilation. If you're multiplying by a positive number that's making it increase faster, it changes the slope, if you will. They call that a dilation factor. It could be a fraction, meaning it compresses, but that's all Algebra 2, and so you'll get to it in a minute. But the last value is really what we call a shifting up or down. It transforms the graph directly. So because you're subtracting 1, it means all of the output is below the original graph by 1. So we see this original graph, okay, and basically what it looks like is that whole graph is just shifted down 1 unit. And so it's going to ask us some other questions about, what about domain and range and all that. Well, I want to go to a graphing calculator and just explore this with you for the last few minutes of this video. I thought domain and range was pretty difficult when I was in school, and so I want to hopefully I can just solve a few ideas that maybe you haven't thought about before, and if not, honestly, it just takes time. Sometimes you have to hear things different ways from different people. So if you were to plug in 0, like the value of 4 to the 0 power is not 0, it is 1. And that really follows, like, there's not a number in the front of this that's multiplying. So that is your invisible 1, that is your y-intercept of 1, and so that's another reason why that point is there. When I plug in 2, you get 16. 4 squared is 16, or 4 to the 3rd is 64, and so forth. But if you notice, these numbers are getting so big so quickly, and I just keep on plugging in numbers and just kind of skip ahead. And then when I plug in 11, it's like, whoa, what's wrong? Is 11 not okay? Can you not do 4 to the 11th power? Well, of course you can, but in the window, I've basically restricted my input and output to be only -10 to +10. So if I want to plug in 11, I now need to make this a little bigger. I need to make it 15. And so you'll notice this axis is increased, and here we go. Now, if you're bothered by not seeing, like when I plugged in 5, and you're like, where's that point? Well, that would be if you needed to change the y. You're trying to change a different axis. So maybe I want to see like -10 to like, I don't know, something crazy. Let's do 10,000. I don't know. But now when you plug in 5, you can actually see that particular point now. There it is. 5 gives you, 1,024, or 6 gives you, 4,096. Now, I can plug in 11, like I was saying a minute ago, because I've got more of an x-axis range, and see, I can go all the way to 15. But as soon as I plug in 16, it's like, hey, you got a problem. And so it's because the window needs to be adjusted. I'm trying to plug in something that exceeds this x-min, x-max window range. Now, it's just not true for the y-min and max. Those stars won't appear, but it'll still tell you that overall value. So I'm going to reset the calculator. Zoom 6 puts us back in a normal looking window. And let's explore it going left now, because left is, I think, way more interesting. And so again, we start with 0, gives you 1, and if you scroll left and right, it's going to give you just crazy irrational points for the input of x, and so it's not going to follow some linear trend like you'd hope it would. If you wanted to plug in -1, you can see that input output. That's actually 1/4. So plugging in a negative, you think about 4 to the 1 is 4. Well, plugging in -1 made it divide by 4 instead of multiply by 4. And I can prove it to you. If you plug in -2, you get this value. That's 1/16. I'll even show you in the output that that's the same number. On the left side, so -3, if I keep plugging in negative values, what's happening is I'm taking that 1 that we started with, and I'm dividing by 4, dividing by 4, dividing by 4. And if you think about how many times you could like cut a piece of paper, I divided it by 4. Okay, now I'm going to divide that by 4. Well, now I got to divide that by 4. Well, eventually I've got a problem in my physical world that I'm having trouble holding this piece of paper. But with the right tools, like microscopic knives and microscopes and stuff like that, I could continue to divide this by 4 until the naked eye couldn't see it, but it would still be there in some physical amount, because you can never cut something that has started with some amount and divide it and all of a sudden both sides disappear. Think about it. How are you going to just divide something? Even, I don't care how small it is, but like if you were to cut it in half, all of a sudden both sides are just gone. And so the truth is that this never hits 0. If you keep going left and plugging in further and further negative values, you just keep getting smaller and smaller values. Eventually you start getting numbers like this. That is scientific notation. If you notice that E, you're saying you're having to do 0 5 times in front of that 7. So it's like 0.00007. And that's, again, just very tiny output. So it's barely above the y-axis. It looks like it's touching, but it is above it. It never actually gets to 0. So when we're looking at our answer over here for domain, when we say the domain is all real numbers, what that really means is you can make up any number. It wouldn't matter what number you plugged in, you would get something out. Okay? I could even plug in pi. I get something out. Or I could plug in an irrational square root of 2. That number is crazy, 1.141. I mean, it's just a crazy number, but it still is possible to say 4 to that irrational power. And so the idea of domain is like you can make x anything you want. It's all real values, as long as you're not plugging in an imaginary number. I'm just curious, what happens when you try to plug in an imaginary number? Ah, see? Because that's the only rule. You can't actually plug in negative numbers. Or, sorry, imaginary numbers. You can definitely plug in negative numbers. Don't hear me saying that. Now, the range, when we think about the range concept, we're thinking about, okay, from the shift down, I think this is all asking about c of x. So maybe I should go in here and shift the graph down by 1 because it was f of x minus 1. And so let's see what that does. Basically, every point shifts down, but we still have that exponential growth there. And so when we talk about the word asymptote, we're saying, like, is there a line that represents a barrier that it would never actually cross? And that's kind of what I'm talking about here. It's this -1 that I can't ever get. When you're in calculus, we'll talk about how it approaches -1, but it never actually touches -1. And so that's why when we talk about the range here, we're saying, hey, all the values are greater than -1. You can get a million, a billion, a trillion, a zillion, make up a number going up, it touches that number for some input. But when you talk about like what you can get out, it's restricted because it's not linear. It's not like it goes up and down forever. It kind of curves off and then approaches this line of -1. Let's just put in that value. I'm going to graph a second line. This is the asymptote line. This represents a line that this other graph approaches. And I know it looks like they touch, but they do not touch. They get closer and closer and closer, but they never actually touch. And so that is the concept of range and domain and range, specifically with that idea of asymptote. And so I hope this video was helpful. If you have any questions, again, you can email me at andrew.turner@knoxschools.org. And again, I really appreciate you watching.